Okay, let me thank the organizers and those involved in organizing the meeting. It's probably a time-consuming task to put this together. Parmita and I feel honored to give this presentation in such a distinguished setting. So Parmita and I will share the presentation. I give the first half and she will take over at the halfway point. So the topic is functional models for time-varying random models. And let me start with random objects, which is the focus of the talk. I will talk about time-varying random objects, but first of all, we need to think about random objects themselves. So I define random objects to be random variables that take values in a general metric space. The space is denoted by omega, the metric by d. There is also a probability measure on that space, but we will not really emphasize that. So the idea is that generally this metric space is not a vector space, and also it does not have an underlying manifold structure. So when it is a vector space, it's a special case that we will also discuss. Here we can have the easiest special case is RP. So you are in Euclidean space and your space is RP. The metric is the usual Euclidean metric, It's the usual Euclidean metric. And this will always be kept in mind as sort of a very important special case. We actually aim to strictly extend methods from the Euclidean case to the metric case, which is not unique Euclidean. So why is this of interest, this topic? Because from a statistical point of view, there are not that many methods available for random objects in general. There are, however, many data which fall into this category, and there are many open problems from a statistical perspective in both theory and methodology. So there has been some work in machine learning on this. However, the emphasis there is somewhat different, less on inference or interpretation of data and more on prediction. So I think this is a rich area this for statisticians to get involved in due to the many open problems. So let me give you some examples for random objects. The first one would be random measures, where we can consider, for example, one-dimensional distributions, which are our random objects. And in this case, we of course need to discuss also what metric we put on the space of random measures. A very promising method is the Wasserstein metric. So in one-dimensional case, this is very easy to define. We can take the Wasserstein metric between two random distributions as the L2 distance between the quantile functions. So this has been a concept which is both theoretically and practically very useful. A second example we will discuss is the space of covariance functions. Covariance matrices of fixed dimension with uniformly bounded diagonals and a related space of graph Laplacians or adjacency matrices for networks with a fixed number of nodes. In both spaces, the simplest metric is the Frobenius metric for such matrices, but of course you can also have fairly complex other metrics, such as the Brogast's metric or Frobenius power metrics for covariance matrices. So we are not operating in a vacuum. There has been previous work in statistics on this. So there is something called object-oriented data analysis, for which a review is a paper Maron and Alonso 2014. In fact, Steve Maron, Channing Wang, and myself, we organized a one-year workshop at SAMSI Institute in North Carolina in 2010, where this was the theme. And a lot of developments actually originated from there. Then a similar concept is distance correlation, which was first of all restricted to random vectors, but since about 2013 with the Lyons paper has been extended to metric spaces. There is also interesting concept by Faraway, 2014, distance matrices. And then we have developed something called Fréchet regression, where you have Euclidean predictors and random objects as responses, and you want to regress the random objects on Euclidean predictors. So these are facets of these fields. There's more, which I didn't mention here. It's just a random selection, as it says. So what are random objects of interest that have been studied recently? Of course, covariance matrices. That has been a big topic over the last decade or so. Dryden has written many papers on it, starting, for example, with a 2009 paper. There is a paper also recently by Tavakoli, John Aston, and others, where a power covariance metric is applied to study language, dialects, to be precise, in the UK. Then a second big area is what I already mentioned, the random measures. Distribution densities. There are papers by Bigot and also Panaretos and Simmel. They have also review papers on this. A third area which we will touch upon is networks. There's a paper by Chinested et al., which views also samples of networks and develops some inference for that. So there are a lot more than these three examples. You can think about trees, shapes, and all kinds of other data as well. So here, just a plot of distributions. These are for Alzheimer's subjects, which we have studied earlier. So each subject, you look at a brain hub, and you measure the fMRI signal of about 1,000 voxels in that hub. You take the correlation of the fMRI signals. So the x-axis is going here from 0 to 1. And then you look at the distribution of these correlations over the brain hub. So each subject has one distribution. All are Alzheimer's patients. What you can see here is it goes all over the place. Some of them have no correlation, almost they are near 0. Others have a peak at 0.5 to 0.6. Question is, can we learn something about the subject based on this, about their mental state? This is an example of networks, which we'll discuss more later. In New York, you take 10 locations and a taxi transports between those. This is a public data set. Everybody can play with it. Here at 3 different times, 12 a.m. on the left upper, 8 a.m. on the right upper, and 7 p.m. on the lower one. You can see that at 12 midnight, there's not much traffic. At 8 a.m., there is some hubs are connecting, and at 7 p.m., structures are also highly connected but changing. Those, so for example, 3 to 4 is only in the evening connected, but not at other times. So this gets me to the actual topic, which is time-varying random objects, because as you have seen, these networks are basically over time of the day, and we have now many days. We can do this for every day of the year, for example. The data actually is available for that. So you have here a network-valued stochastic process. In general, a metric space-valued stochastic process over a time domain, and we have a sample of such processes available. That's the general structure we are studying. For theory, which I will not expose here much, we draw an empirical process theory for our proofs. These are, the details are in the paper. You can look it up there. Now let's discuss the special cases that have been studied before. As I mentioned, Euclidean case is always a special case. Simplest one is scalar, R1, right? So in this case, we have functions which take values in R1. That's the main topic of functional data analysis, which has been actually around since 1950. And then started that. Statistically, it got active only around 2000. Ramsey's book, Ramsey and Silverman 2005, review article recently. There is then a multivariate version. The functions take value in RP. That's called multivariate functional data analysis. So the idea is you always have a sample of those things. Multivariate functions have a sample of them. And then you can also think about function value stochastic processes where your space is L2. So it's a Hilbert space. That means we are still in a Euclidean setting. And we can then use, for example, the L2 metric. So we have a stochastic process at each time it takes a functional value. These data are quite common in longitudinal studies, actually. Okay, the next step is we go away from the linear structure, Riemannian manifold, where you can locally linearize things. Here, the metric is usually defined through geodesics. This has recently become active in various ways. So think about you fly from London to Hong Kong on a plane. The plane takes a certain trajectory on the sphere, which is the Earth. And you have now 100 flights. You want to know what's the general structure of those flights. That can be analyzed by putting tangent planes around the means as we go forward, the means of all these flights in time. Put a tangent plane, we go forward, and in each tangent plane we do some sort of a principal component analysis. That is the case when we have manifolds. So manifolds are not linear, but they're not too far from linear because we can locally linearize them. The challenge we address here is when you don't have a manifold and you don't have a Euclidean space, that means no vector space, even not locally. So that's the real challenge. So here, a summary of the challenges. Traditional functional data, okay, x of t is in R. We talk about smooth random functions. Samples of smooth random functions, we do things like functional principal component analysis, which are well established by now. Now we are thinking about functional random objects. So our trajectories are in a metric space omega. We call this a random object trajectories. And then how do we proceed in functional data analysis? A key is the autocovariance surface because you need to quantify the dependencies of your process at different times, which is done through the autocovariance. And then the question arises, what can we do if we do not have a metric, if we don't have a Euclidean vector space? What's the metric equivalence? That will be the first challenge, which we call metric autocovariance. The second challenge is here, what can we do an eigendecomposition, which we do in the functional case, where we decompose the autocovariance surface into eigenfunctions and eigenvalues. Is there something like that? That's the second challenge. The third challenge is finally, can we represent our functions in some way, like we do in the linear case, where we say the function is the mean plus an expansion in the eigenbasis. Okay, so this is a basis expansion of my random process X, which has proved very useful in applications. You usually truncate this expansion at k elements. Is there something like that when we don't have vector structure? Our answer is, our approach is Fréchet integral. This will be presented later by Paramita. So let me go, we walk through the three challenges, okay? The first challenge is covariance. That means how do I quantify dependency of metric valued processes. So what we did is we introduced a new covariance correlation measure for random objects in general metric spaces, which we need to obtain something like autocovariance. We want this extension to be contiguous to the Euclidean case. What that means is In the special case of Euclidean data, it should go back to the usual covariance. That excludes something like distance correlation. It cannot be used because it doesn't actually simplify to the usual covariance in the Euclidean case. So how do we proceed? We consider pairs of random objects UV and independent identically distributed copies U prime, V prime. Later on we will set U is x of t and V is x of s. Now let's start with the Euclidean case. In the Euclidean case, everybody knows the covariance between two random variables is given here, the formula is here. Now, we can actually very easily see that it can be rewritten in terms of square distances between variables u and v prime. Remember, u prime, v prime are independent copies, identically distributed of uv. And here u prime v and then uv. So just square it out. These are squares. Euclidean case is just u minus v prime squared. So it's totally trivial to see this. So the covariance can be expressed here without taking the mean. The mean is problematic in metric spaces. We can use Fréchet means. But Fréchet means have the trouble that oftentimes they are hard to compute or also not unique. So we want to avoid means in our covariance, which this does, right? This representation of the usual covariance avoids means. Same is true in Hilbert spaces. So if you have a Hilbert space, for example, L2, you can do exactly the same thing. You can express a covariance of Hilbert space valued variables in terms of square distances in the Hilbert space. And that gets us to the idea to define a metric covariance by taking exactly this kind of representation, but now following the lead of Fréchet 1948, who said, okay, in order to take a mean, I cannot take x bar in a metric space, but I can take a minimizer. I can find a minimizing element which minimizes the square distance to all of them. In other words, I replace the Euclidean distance by whatever distance I have in my space, and that's what we are doing here. We are taking the lead from the previous consideration, and we now put just d here for a general distance. And we can also do the correlation this way. So what are the properties of this? Well, let's talk about the variance, which is a special case of the covariance. So you get 1/2 the expected value of d square of u, comma u prime. U prime is the independent copy of u. This, of course, is well known in the Euclidean case because all of you know that sigma hat squared, the sample variance, can be alternatively expressed as a sum of the square distance between the data. That's exactly the same, right? So we get something which makes a lot of sense in the Euclidean case and which works in any metric space as well. And then we also, okay, I mentioned already it doesn't require means, and the usual interpretation of a covariance is given also as well as that this metric correlation is between -1 and 1 if we make one more assumption on our metric space, which is that it has to be of negative type. So next challenge, where this negative type will be more explained, is the eigendecomposition, which we want for our metric autocovariance. We have now the metric autocovariance, but can we get the eigendecomposition? For that one, of course, we need that this covariance is non-negative definite. It is symmetric, but it needs to be non-negative definite. So we have to show this somehow. It turns out that if we have a totally bounded and separable metric space, so we make that assumption now, that in this case, so that's a basic assumption for all of the following, that in this case, if we have a semimetric space, omega d square, if you start with a metric d square is a semimetric because you use the triangle inequality. Otherwise, the other two properties are there. So we call this to be of negative type if you have a linear quadratic form in these distances, which is formed with alphas that sum to 0. And you have that this quadratic form, which is here, is not positive. So what happens then? Why is this useful? Because if we have a negative type, Schoenberg showed sort of a bit indirectly, but then later exploited by Sendovich in a recent paper, that if you have this negative type, then there exists a Hilbert space, even only if an injective map from your metric space into the Hilbert space such that the distances in your metric space can be expressed equivalently as distances of the mapped objects all squared in the Hilbert space. The Hilbert space, however, is not known. Neither is the map. We don't have this. We only know it exists. But that means that our covariance, our metric autocovariance, does have the interpretation of a covariance in an unknown Hilbert space. And that gives us a lot of ammunition to carry forward, for example, the metric autocorrelation to be between -1 and 1, and also to move forward with having a non-negative definition of the metric autocovariance operator. So if we now define for omega valued random curve x of t our metric covariance between x of s and x of t, remember these are metric space valued objects at 2 different times. And if the semimetric d square, which belongs to the metric space, is of negative type, then we can be assured, because of the existence of this map, that we have a non-negative definite kernel, which then means that the operator, the linear operator which uses this kernel, is a linear trace class operator, and it has an eigendecomposition with non-negative eigenvalues and also normal eigenfunctions. So what happens is we now solve the second problem. That means our metric autocovariance operator allows us to define actually a spectral decomposition in eigenfunctions and eigenvalues. Eigenvalues will be non-negative. And so here is the decomposition of the autocovariance kernel function CST. The total variation can then be written as the integral over this variance at each t, the covariance of x of t with x of t, which is the metric variance, and it can be written as 1/2 the integral e of expected value of d square x of t x prime of t. And the eigenvalues, which we got now, provide a metric version of the fraction of variance explained along metric eigenfunctions. So we can do a scale plot, for example. Now, estimation is another story. I will be brief with that. The details are in the paper. We estimate this metric autocovariance function by taking basically objects xi, xj, which are independent. Remember, we have an independent sample. And we plug into the formula you have seen before, the definition. So we plug in these estimators. We divide by n squared. We have pairs, right? Essentially, and then we do an empirical spectral decomposition of the resulting estimated autocovariance kernel. So that follows standard procedures once we have this. Now, if you want to analyze this in terms of its properties, this estimator, that is, we realize that what we have is a function indexed U process where we have this function class fst, which is defined here, actually down here. So we have to utilize results from function indexed U processes which were developed by Nolan and Pollard. And then with that tool, if we then assume a smoothness condition of some sorts for our metric valued stochastic processes, namely assuming that the distance between 2 points, time points s and t if it's time, is bounded by a Lipschitz condition times a random variable of x, such that this random variable has a finite second moment. Then, if we also have an eigenvalue gap condition, that means the eigenvalues are first of all of multiplicity 1, and secondly, they have a certain spacing. Then we can show that the standardized U process, which is the process we have to consider in order to look at the asymptotic of C hat, that this converges weakly to a Gaussian limit process with mean 0 and a covariance function which we can calculate. And if we also have the eigengap value condition, then applying the Davis-Kahan theorem in a form obtained by Bosk in 2000, then we can get convergence rates for the estimated eigenvalues as well as the estimated eigenfunctions for our metric autocovariance operator. So let me briefly show an application. We have 32 countries from 1960 to 2009. This is, again, a public data. Xi of t will be now a process which is distribution valued. So at each time, which is calendar year, I have a distribution of h at des for these countries in the years 1960 to 2009. So we have exactly the situation I was describing. We use here the Wasserstein metric, which I also already introduced before, because these are random measures, right? So here, just a sample of 4 countries. These are the males for 4 countries. You can see the countries behave quite differently. You have calendar year going forward this way, and h at des this way, and this is the distribution represented as a density here. You can, of course, also represent it as a hazard function or whatever you like. You can see big differences between Russia on one hand, USA on the other. Portugal has a super high child mortality in 1960, which declined now to smaller than the US, which is sort of pretty high among those 4. US is higher than Russia, actually, for child mortality, as you can see here. So this is our data for males, and here is the same for females, where, interestingly, Russia looks more similar to the US, as you can see, for females. If I go back for males, you can see a huge difference. For females, this difference is not there. The structure, at least, is much more similar. So this is reflected in terms of the metric covariance surface, which we can calculate according to the formula before. You can see that for males on the left, there's a lot going on. The variance is actually very high in some areas, especially around 1990s and subsequent. And the question is, why would that be? For females, nothing like this, right? Females have a high variability in 1960, and then it just goes down. So what's happening? Well, what happened is the collapse of the Soviet Union, and all the Eastern Bloc was affected by this, and it turns out that males were mostly affected, females by far less. So that's, in a simple phrased explanation, why we see these very different covariance structures, autocovariance structures, with our metric autocovariance. We can also, of course, then show the eigenfunctions. They are quite similar between males and females. There's not a huge difference. The first eigenfunction here, for example, is just the overall level of mortality. And then you differentiate what happens over the years. Here, for example, the first one is mortality early versus late, and so on. So now we come to the last challenge. Namely, remember, we wanted to represent these functions by some representations.
Okay, so we tried to resolve the 3rd challenge here through an approach called the Fréchet integral. So even for the Euclidean case, the FPCs are very useful because they reveal a lot of important patterns going on in samples of functional data. And we would like to have something analogous for the non-Euclidean case. And, but if omega was a Hilbert space, then the obvious thing to do would be to take projections along the eigenfunction using the inner product that's available. But unfortunately, we don't have an inner product in our metric space. So what could we do? So here we actually take a closer look at the integral xt psi t dt and observe that Riemann integrals are basically limits of Riemann sums. So when the integral psi t dt integrates to 1, the Riemann sums are basically just weighted averages of xt. So in some sense, we can have an alternate representation in terms of the Euclidean metric, which we can see on the right side. And this expression here depends on xt only through the metric, and so it's much easier to deal with than the object trajectories themselves. And this is where we draw inspiration and extend Riemann integrals to Fréchet integrals, just like one can extend Euclidean mean to Fréchet mean for metric space data. So we'll just take a quick look at what is a weighted Fréchet mean. If we have weights alpha 1 to alpha k that add up to 1, and elements omega 1 to omega k taking values in big omega, then the sample Fréchet mean, the weighted Fréchet mean, is defined to be the point omega which minimizes the weighted sum of squared distances. So having looked at that, we now define the generalized projection of xt on a function psi t integrating to 1 to be the minimizer of the criterion we see there, which we'll refer to as the Fréchet function, this criterion here. And that gives us the motivation also to define functional principal components in the object case, because now we have eigenfunctions which we can scale, provided that their integral is not 0, so we can scale them to make sure that they integrate to 1. And then we can define generalized projection by taking the minimizer of the Fréchet criterion, which is basically the minimizer of weighted Fréchet means. So one point that I want to make here is that the generalized projection resides in the object space and not scalar like functional data. So we'll come to that later. But so here we formally define the functional random object principal components. So for the ith subject, if we have the omega valued trajectory xit, then we define its projection on the eigenfunction phi k to be the generalized projection on the scaled function phi k star. And estimation of the Fréchet integrals is very straightforward. We just use the plug-in estimates of eigenfunctions of the estimated metric covariance operator. And luckily enough that these Fréchet integrals have the benefit of being limits of M estimators. So basically we can tap into the theory of M estimation to establish their consistency and also obtain a rate of convergence. So under basic assumptions like existence and uniqueness, which is standard from the theory of M estimation, we can show that the Fréchet integrals are consistent. And additionally, if we have a curvature condition on the Fréchet criterion function, then we can derive a rate of convergence in terms of beta 1, which also appears in the curvature condition. So here, we will like to demonstrate some simulation results. So the point of the simulation is twofold. Just one of them is to show that as sample size increases, the estimation gets better of the target properties, but that's kind of obvious. So we'll not talk, I'll not focus on that. What I'll focus on is basically to illustrate how the Fréchet integrals look like in this case, which kind of will help us to intuitively view the concept of Fréchet integral. So here we take a sample of univariate distributions with the L2 Wasserstein metric. So the sample of object trajectories in this case are xit, and xi of t at each t is a normal distribution with a random mean and a random variance given by mu it and sigma square it. So mu it is generated randomly using the orthonormal functions phi 1 and phi 3, and sigma square it is generated randomly using orthonormal functions phi 2 and phi 3, and then we have random variables loaded on the eigenfunctions which are uniform and have different degrees of variation. So we generated 100 such samples and estimated the metric autocovariance operator each time and evaluated the performance using the mean integrated squared error to the target metric autocovariance, which we can evaluate in this case because it's a simple situation. We have Gaussian distributions and the Wasserstein metric, so everything is known. So we can evaluate what the target autocovariance will look like. And in this case, phi1, phi2, and phi3 in that exact order turn out to be the three eigenfunctions in that order. So we are able to show that the estimation errors go down with increasing n. But what's more interesting is how the Fréchet integrals look in this case. So I'm going to take some time here to explain what are the red curves and the blue curves. So here we plotted the Fréchet integrals for a sample of size 50. So we have 50 red curves and 50 blue curves. So each of the red curve is a Fréchet integral of a sample of distribution valued trajectory with respect to the first eigenfunction. So they are the first principal components in the object space. And we see that the variation in the densities arises through their location, which intuitively makes sense because we are taking projections along phi1, and the only thing in the densities which loaded onto the phi1 was the mean function. The variance did not in any way have phi1, and it was actually orthonormal in some sense, the random part of the variance. So that way the variance of these densities come from their location. And we can see an exactly similar situation going on for the blue curves. So each of the blue curve is a Fréchet integral along the second eigenfunction, but in this case the variation is along their scale and not on the mean. So we go back to the mortality data where we had samples of time-varying distributions for many, many countries, and we constructed the Fréchet integrals, and each of them is a density. The blue ones here correspond to the non-Eastern European countries, and the red ones correspond to the Eastern European countries. So we see that for the males, there is a clear difference in how the Fréchet integrals look like. And the black curve here is Portugal, which kind of stands out even amongst the blue curves. So it's kind of like an outlier. But for the females, we see that the black curve stands out, but the blue and the red curves do not show that much of a difference. So to sum up with the concept of Fréchet integrals, they could be useful as summary measures to represent samples of time-varying random objects. And like in the Euclidean case, we use the functional principal component scores for lots of things like clustering or detecting outliers, or even for regression. We can utilize the Fréchet integrals in recently developed approaches where we have regression setting of object data as response and Euclidean predictors, and also distance-based clustering and classification approaches to get some meaningful interpretations on the sample of object trajectories. So basically, the only challenging part of the Fréchet integrals is sometimes they could be very tricky to visualize. Like for the densities, it's not that big of a problem, but if we had more complex data like networks or covariance, it's not very easy to visualize, and we can't tell apart which one is an outlier straight by looking at them. So one option is definitely to project these objects into the Euclidean space using some multidimensional scaling approach that will give us some visualization. But that may not, that could be useful, not be useful, but we take an alternate perspective in terms of another thing which we call Fréchet scores. And the lucrative part about this is it has nice visualization because these are scalars. So here we again, so far we were talking about a mean-less approach, but now we actually look at an approach where we start from the Fréchet mean function. So the point-wise Fréchet mean function basically is a central notion of a trajectory, like the random trajectories. So we look at not the object functions themselves, but the distance of each object trajectory around the Fréchet mean function, which kind of gives an approximation of how xit varies around mu it. And then we decompose this distance function in the eigenbasis of the metric covariance operator. So the eigenbasis decomposition and these scores actually give nice representation to view how the object trajectories vary around their mean function. So I'm not going into details of estimation and theory because we have very less time left. I'll just like to illustrate the Fréchet scores through an example. This time we have time varying taxi trip networks. So yellow taxi trip records are available for, in Manhattan, and it's a very rich data which is publicly available, and we only consider a very special case of it. So we basically club the zones in Manhattan into 10 broad zones, which are our zones of interest. And between, so using these 10 zones, which we treat as nodes of a network, we construct a time-varying taxi trip network where the xi tilde of t is the graph adjacency matrix, whose k-lth element is the number of people traveling between zones k and l at time t on the ith day. And then we basically scale the total number by the maximum, but by the daily maximum across all entries, just as a normalization step, but that's not a necessary step. One could avoid that. As data, we took the normalized graph adjacency matrices, and we work with the Frobenius metric. Again, that's also an open question, and there could be several interesting metrics to work with, but that's not, we are not going into that now, but definitely an area to explore later. So here is a snapshot of a typical working day, where the first one is a network at 8 a.m., the second one is noon, the third one is 4, and they don't show too much of variation. But 7 p.m., 10 p.m. and midnight are very different. So it seems people take more taxis at 7 p.m. and 10 p.m. and then it begins to become sparse again at 10 p.m. So we have this is one day, but we have 363 days. We had to remove 3 days from that year because they were not complete records. So we have 363 such samples of time evolving networks, and we look at the metric covariance, which again gives very intuitive results, because we see that the night time, 12 a.m. to 3 a.m. is negatively correlated with the peak morning commute time, and then again with the evening commute time. So it's kind of intuitive from what we can imagine, and the eigenfunctions also are peaked around the morning commute mostly and show contrast for different timings of the day. So what I really want to illustrate here is the Fréchet scores this time, and we see very meaningful patterns in the data, because weekends and weekdays are very nicely separated. Even Fridays are separated from the weekdays. So there are some special like days. The black dots amidst the red squares are basically some special holidays, like which fall on Mondays and Fridays, like Memorial Day and Independence Day and things like that. And then we have some special days like 1st January, the New Year's Day, the 4th of July, which is Independence Day in USA. 6th November is the day when daylight savings time ends. And 14th February is Valentine's Day, when couples may be visiting each other. 30th October, that year turned out to be just the last Sunday before Halloween. So all these days have special meanings. 18th September, it has no special holiday association with it, but when we look back, there was a series of bomb explosions in New York on that day in that year, so it is indeed a special day. So all these patterns are revealed using the Fréchet scores. So just as concluding remarks, I'd like to add that thanks to all kinds of latest innovations, we have new kinds of complex data coming up more often than ever. And as statisticians, we should be like also innovating both theoretically and practically to come up with sound methods with also solid theory backing to handle such data. So I'd just like to let Hans show us a picture.
This is the last picture, which shows a negatively curved manifold, a Hadamard space in front. So here you can do local tangents if you want. But behind, you have a metric space. There's no tangent space there. So this shows some cases where we can do local tangents in the foreground. In the back, no way. So you have just the whole space is convoluted, and that would be a metric space where manifold approximations don't work. So that's what it's supposed to show graphically.
Okay, so let's start. So thank you very much for the very nice presentation and the paper. So it's the first time I'm being a proposer, so I hope I will follow tradition more or less. So what is, let me just put the paper in perspective briefly. So in functional data or random object data, data points are either like real vector valued or Hilbert space valued curves, okay? But they can also sometimes be covariance matrices or operators, so each data point is an operator or each data point is a matrix. Each data point could be something more complicated, such as a measure or a density function. And data points can also be something much more exotic, such as trees, for instance. Okay? So if you just, I'm making everything very simple, and I prepared this on the train coming here, so I didn't put any references. Hans did put all of them, so you saw who did what, more or less. But roughly, you have 3 categories of functional data. One is you're in a Hilbert space. And a Hilbert space is nice because you have distances, you have directions, you can move in directions, and you have a geometry, you have inner products. The second category is less nice. It's essentially Riemannian manifolds. So these spaces are not Euclidean anymore. They have curves. But the nice thing is you have locally at every point, you have a tangent approximation. So you have a linear Euclidean space approximation locally. So you have a distance, but otherwise you have just local Euclidean approximations. Locally you can move in directions, and you have a local geometry. And then all hell breaks loose. You have a metric space, and the only thing you have is a distance. You give me 2 elements, I tell you what the distance is, and you have to work with that. Okay, so what's the nice thing about having a geometry like in the first case, or a local geometry like in the second case, where, well, you can do moves in certain directions or local moves in certain directions, and therefore you can do PCA or local PCA, okay? And that's really the workhorse of functional data, because your objects are functions, are complicated things, so if you want to understand them, PCA is a nice way of summarizing their variations, okay? Behind PCA, there is the Caron-Lev expansion. Good. If you only have the distance, then what does it mean? If you're in a metric space, what does it mean to move in a certain direction? It's not really clear, okay? So how do you do PCA? And what Paramita and Hans have come with is a way for doing PCA for time-varying random objects. Okay, so x of t is in omega. Omega is a bounded metric space, and t is on the unit interval. And the main question I'm quoting from the paper is, we aim here at identifying dominant directions of variation where random objects are indexed by time and are in general metric spaces. Okay? So now, this means what? Well, you want to define some kind of functional or object PCA. You want to understand what main modes of variation is. you want to do pairs plots because that's something really useful when you're doing PCA. You want to look at pair plots, okay? And then, I mean, you can define these for population, and then you have to estimate them. So does it work or not, okay? And so I saw Hans's slides, and I thought he managed to somehow get my slides before I finished them. So essentially, I'm going to go back on what Hans said, but I'm going to point out a couple of things, okay? So if you have real valued functions, so x of t is real valued, then the covariance kernel, which is really the workhorse for PCA, is C of ts is the covariance between x at time t and x at time s. Now, what is the covariance between two random variables? Well, it's this thing. You have differences and you have products, but you can re-express everything in terms of distances. Okay. So that's nice because now I can take directly this formula and I can plug it for more complicated things. So if I have now random vectors, I can take the covariance between these random vectors as defined by this formula here. Okay. And you notice that this thing is what? It's the expectation of the inner product between these things. So it's not the usual covariance, because this thing is real. Okay, so this metric covariance is real, but the usual covariance is a matrix. Okay. Good. Now, if you're in a Hilbert space, well, it's essentially the same thing, but you just have to adjust the notation. The metric covariance is like the covariance, but you have an inner product here instead of a tensor product. So it's not, again, the usual covariance between two random elements. Okay? But then what you do, you have this nice definition in terms of metrics. So in a metric space, you just define the covariance using this equality that only involves distances. And now the question is, does it correspond to something like this, an expectation of an inner product? Well, you don't have inner products, so forget about it. But I can define this covariance, metric covariance between S and T. The problem is, if I just define it like this, it's not guaranteed to be positive definite or semi-definite. That's where you need the assumption that the metric space is of negative type, and then you can justify that this covariance kernel is indeed positive, semi-definite. So now you can just do the usual PCA ideas. What are the PCA ideas? You assume that you have the autocovariance kernel that is continuous, so it's not made precise in the paper, but you need continuity. Okay, and now you have a decomposition of this kernel in terms of eigenfunctions and eigenvalues. And usually what you do is you compute these scores, for instance, by taking integrals of your function x with the functions, the eigenfunctions. You cannot do that here. Okay? So the authors have a couple of ways of getting around this. They define something called object FPCs, which are like the scores, but now they are in the metric space. So it's nice because instead of having a curve, every observation being a curve, every observation is just a couple of objects in your metric space. If you don't want to do if you want to do pair plots, you can compute Fréchet scores, and this gives you numbers, and now you can do pair plots. So, how much time do I have left? 2 minutes? 2 minutes. So, what were the main aims? You wanted to have a method in general metric spaces, and you wanted dominant modes of variations. But the thing is, all the examples here have a richer structure than a metric space. We have densities, we have networks, we have covariances. You can make operations on these. Okay? If you only have a metric, you can compute the metric covariance. And you can get the eigenfunctions, but you cannot really compute the object PCs or Fréchet scores because you have to do a minimization. And typically, as far as I know, minimizations, you need to have an algorithm, such as gradient descent or something. The other thing is, in metric covariance, you're losing a lot of information. So the metric covariance between U and V, if you're in a separable Hilbert space, it's the trace of the covariance between U and V. Okay? And that's not a good measure of the magnitude of the covariance. unless the covariance is positive, symmetric, and semi-definite positive. Okay? So here's is an example. I take a process u of t that is real valued for t between 0 and 1/2. And now I define x of t that is vector valued. In the first half interval, I put u of t in the first coordinate. In the second, I put u of t in the second coordinate. And then suddenly, if you compute the metric covariance between t and t plus 1/2, it's 0. But the true covariance is not 0. So there's a small problem here. If you look at modes of variations, you don't really have the interpretation that you're maximizing the variance of the projection. And that's when you look at a Hilbert space. So you cannot just apply the method and it does the same thing as what you usually you're used to. Okay? The Fréchet scores you get in the real valued case, it's not the PC scores we're used to. So you just have to be careful about that. Some extensions, you don't have to have t that is in an interval, you can have it on a domain. You could work with the full covariance by using the implicit injection given by negative type metric spaces, but it's not clear how to do it. So to finish, I'd like to conclude, it's a really nice paper because it moves beyond the usual notion of covariance, because usual covariance is all about linear dependencies. And Jim Ramsey said in 2010 at SAMC, in 2016 at Diablerets, we need to move away from that a little bit. So this is pushing us, this paper is pushing us in that direction. So I propose the vote of thanks.
So thanks very much for an excellent presentation, and I would also like to congratulate the authors on several substantive conceptual and theoretical developments in their contribution. So among them is a new association measure termed metric covariance, and beyond that they also develop a whole framework of functional principal component analysis using generalized Fréchet integrals for time-varying object data. This framework hinges on the introduced association measure, so in this presentation I will be focusing on the association measure itself. But I want to emphasize that these are both elegant contributions and will undoubtedly lead to a widely used methodology. Okay, so I will focus my discussion on metric covariance, and in particular on its relationship and connection with other similar concepts which have previously appeared in the literature, including already mentioned distance covariance of Fréchet and co-authors, and corresponding generalizations which rely on the formalism of reproducing kernel Hilbert spaces, RKHSs. Okay. So let us just remind ourselves of the definition of metric covariance. So we have a metric space, omega d, such that d squared is of negative type, so a square of the metric. Then metric covariance is just given by this expression that we've already seen, which has a nice property that actually just generalizes the usual notion of covariance in one dimension. So what is this notion of negative type? Well, that signifies that one can actually find a particular Hilbert space H and a mapping phi, which I will call feature map, going from our metric space to this Hilbert space, such that the square of the metric is just the square of the Hilbert metric. Okay, so because this is just a square of a Hilbert metric, we can put it back into the original expression for the metric covariance, and we see that the notion of metric covariance simply corresponds to a difference in expectations of the inner products between feature maps under the joint and under the product of the marginals. So if we think about inner product as some notion of similarity, it will consider if x and y are on average more similar in the coupled regime than in the uncoupled regime. And importantly, this quantity can be both positive and negative. Okay? So on the other hand, there is this other notion called distance covariance, and it takes the following form. So here we actually allow random objects to take values in different domains. So we have two semimetric spaces of negative type. Rho here takes the role of d squared in the previous slide to make the notation consistent with papers on distance covariance. So in that sense, we require rho only to be a semimetric, not a metric, because it need not satisfy triangle inequality. As you see, this expression is actually much less intuitive, and it does not seem obvious that there is any link to metric covariance. However, there is a more straightforward way to understand distance covariance using reproducing kernel Hilbert spaces, and it's based on this notion of embedding of probability measures into RKHSs. So if we just define an embedding of a probability measure P as this Bochner integral of k dot x, where k is any positive definite kernel, then we can recover distance covariance by relating positive definite kernels k and l to our semimetrics of negative type rho x and rho y, and then view distance covariance simply as the squared Hilbert space distance between the embedding of the joint distribution and the embedding of the product of the marginals. Okay. So this view actually comes from the machine learning literature, which is sort of the world I inhabit. And here it can be viewed in different ways, and one more intuitive way is to just say, well, we have data of different types. They are coupled. They can be some arbitrary objects. We can define some notion of similarity on both types of objects. We form a kernel matrix, which corresponds to a similarity pattern on these objects. And then we simply look at how aligned these similarity patterns are. And that is an intuitive measure of dependence. Okay. So there's also an alternative view of distance covariance or this Hilbert-Schmidt independence criterion, which actually hinges on isometry between RKHS H corresponding to the tensor product kernel between kernels K and L, and the space of Hilbert-Schmidt operators between HK and HL. So if we define the cross-covariance operator sigma yx that maps from the RKHS HK to RKHS HL, such that G sigma yxf inner product actually uncovers the covariance between f of x and g of y, where f are and g are any two RKHS functions, then distance covariance, or this notion of H, just corresponds to the Hilbert-Schmidt norm of feature space cross-covariance. Okay. So for broad class of choices of these kernels, KL, which are in machine learning literature called characteristic kernels, this notion fully characterizes statistical dependence. And there is a large number of these kernels that can be used, including Gaussian kernels, Matern family, and various others. Okay, so what I'd like to address is whether there is also a corresponding RKHS interpretation of metric covariance, which might shed light onto its relationship with this object. Okay. So we will recall that in this context, domains of x and y actually coincide. So we'll just consider a single metric space with a single metric d. D squared will be a negative type, and we will associate to d square a positive definite kernel in the following way. So omega here is just some arbitrary anchor point that actually doesn't really matter. Okay, so we will denote by HK the RKHS of kernel K. And now we have again this cross-covariance operator sigma yx. Now it goes from HK to HK. And it is readily shown actually that metric covariance simply corresponds to the trace of this operator sigma yx. So Shaheen has observed something very similar in his talk. So in contrast, we recall that distance covariance is actually Hilbert-Schmidt norm, squared Hilbert-Schmidt norm of this operator, which is trace of sigma yx, sigma xy. Okay, so the proof of this is actually trivial. It just hinges on linearity of trace and the fact that the trace of the outer product is the inner product. But now we can sort of try to understand a little bit more the properties of metric covariance, and in particular when it is actually zero. And Shaheen also gave an example of that, so we had a very similar line of thought. So a straightforward example is to say that x and y are actually dependent, but their feature representations live in orthogonal subspaces. So we can just take a linear kernel on R squared and then have x be z node and y node z. So there's now a deterministic relationship between the two, but of course metric covariance is 0. So now, of course, this is with respect to a very specific metric, which is Euclidean metric, that corresponds to the linear kernel, and it doesn't actually occur if we choose other metrics on the space. So there are alternative interpretations in terms of Mercer basis. So if we consider Mercer basis of corresponding RKHS, then we can simply uncover metric covariance as this expression on the right-hand side there. So it's sum scaled with the eigenvalues corresponding to the integral kernel operator, so those are not too important for this discussion, of the covariance between EJX and EJY, and EJ are some basis functions of L2. So in particular, we need the evaluations of X and Y to covary at the same basis functions. So we can make the 0 if none of the evaluations at the same basis function covary, or if somehow positive and negative covariances between basis functions cancel out. So in contrast, again, distance covariance looks at covariances between all pairs of basis functions. Okay? And here's, I think, a more a more interesting example of where actually we can get metric covariance to be 0, even though there is a strong dependence between random objects. So again, we're just in R squared. So I will make both X and Y these mixtures of normals. They will be coupled in a sense that the mixing variable is coupled. So X and Y will tend to appear in the same half plane in this case, so left or right. Okay? So there is strong dependence, and in particular, if I look at the correlation between dimension 1, it's strong and positive. If I look at the correlation between dimension 2, it's strong and negative. So we're not talking about orthogonality in this context. So, but what is actually a little bit more ominous in this example is that the distribution of the distance between X and Y is the same regardless of not whether they are coupled. Okay, so X minus Y and X minus Y prime have the same distribution, which means that if I take this kernel view and I'm considering what kind of kernels will actually detect this dependence, well, none of the kernels that are radial in the sense that they depend on these Euclidean distances, for example, a Gaussian or Matern, will be able to ever detect this dependence. Even though many of these radial kernels are characteristic in a sense that distance covariance computed with them will characterize dependence. Okay? So just to summarize, when we have this generic choice of metric, the corresponding Hilbert demanding phi is defined implicitly and may not be always straightforward to interpret. But what forms of dependence are actually captured by metric covariance can strongly depend on the form of phi and hence on the associated kernel. But on the other hand, I find this RKHS interpretation quite exciting because it actually may give rise to different estimation methods for metric covariance and the developed framework of functional principal component analysis, for example, by making use of the literature on large-scale kernel methods. At the end, let me just comment that I have found the contributions in this paper very stimulating and pleasure to read, and I'm therefore delighted to second the vote of thanks.
All right, I just want to make a few remarks on a different approach that could be used, which is kernel PCA. So Dubé and Müller consider observations which are metric valued, so the values, metric valued functions, function values are in a metric space. I'll put it slightly more generally over some set T. So I will show how to apply kernel principal components in a well-cited paper by Scholkopf, Smola and Müller, different Müller. I'll show a close relationship with the present method, and I will indicate potentially simpler theory and interpretation of kernel PCA. Okay, so difficulty with the Dubé-Müller metric covariance kernel. This was a difficulty pointed out by the authors themselves. So metric covariance kernel has eigenvectors which are real valued functions over set T. So clearly it's not obvious how to compute principal components of observations which are metric valued functions over T. So there's a disconnect, real valued functions versus metric valued functions. So Dubé and Müller have to construct new concepts, objects, functional principal components, and Fréchet scores, complicating interpretation. So with kernel PCA, eigenvectors are embedded metric valued functions over T, so they are compatible with the embeddings of the observations, and computation of kernel PCs is easier and immediate. Okay, so it's very well cited. I just wanted to make the point it's not cited, almost not cited at all by statisticians, only 0 in the top 300. So let me say a little bit about kernel PCA. We have observations x1 to xn in an arbitrary space. So essentially kernel PCA is PCA on a Hilbert space embedding of the observations. So via the kernel trick, we don't need to actually compute these embeddings. We just need to compute the inner product of the embedded observations, which is a kernel matrix. So the present task with metric valued functions as observations is to find a kernel for metric valued functions. So we can use a useful fact for any metric space of negative type. We have a unique kernel based on a distance preserving Hilbert space embedding. So we need to find this metric for the observations. So how can we do this? So there's a unique kernel, so the same omega. The authors consider unique kernel k omega, lots of literature with examples. So we can define x to be the metric space of omega valued function over T with distance function just the integral of the local distances. I think this is implicit in the author's paper. And then, don't have proof here, simple proof, unique kernel for the observation space is just the integral of the local kernels. So this lemma allows kernel PCA to be done, so we have a metric space of negative type, assuming omega is of negative type. So we can compare kernel PCA versus the author's method. So the kernel PCA covariance kernel is a kernel valued kernel, and the evaluation at ST is that object. So the outer product of the embedded observations, of the centered embedded observations evaluated at S and T. The Dubé-Müller metric covariance kernel is a function of C. It was already pointed out by previous, some similar fact was already pointed out previously, is not the outer product but the inner product of the centered embedded observations evaluated S and T, or the trace of CST. So the eigenvectors of C are metric valued, embedded metric valued functions. And principal components are naturally defined. So the eigenvectors of CBM are functions, real valued functions. So to make things work, we need object functional principal components for Fréchet scores, and maybe this complicates the interpretation a bit. That's it. Thanks.
So there are two features particular to functional data that I think are worth mentioning. And one is the problem of discrete measurements, and the other is the problem of warping. And I think that it would be important to somehow see how can we address them in this general framework. And it's completely not obvious, at least not to me, how to do that. But I think that this would be a very natural and important generalization to think about. And so that's, I think, one of the nice points in this paper is that it really opens the door to many extensions and future work that can and I believe should be done. So that's what I wanted to say.
My name is Rajman Sali. I know next to nothing about the subject area, but nevertheless the thought occurred to me that you should be able to come up with some more summary measures, such as quantiles, medians, which are sort of robust, rather than objects which look like means and variances, which is what you seem to be working with. And they may have some uses when data are collected from, say, infinite variance stable distributions and related objects. Just a simple question.
So for the exploratory analysis, real-valued Fréchet scores are demonstrated to be useful in the application to the mortality, taxi networks, and world trade data. The Fréchet scores, produced by projecting the distance function from the object trajectory to the Fréchet mean trajectory on the eigenfunctions, summarize deviation in terms of distance from the mean. As there might be additional variation, such as rotation around the mean, that is not reflected in the distance to the center, the Fréchet scores could be complemented by, for example, the multidimensional scaling coordinates produced with distance measure, which is defined, which you can't see, between time-varying objects. That's it.
Yeah, just a lot of comments were about the nature of the measure, which is a big compression, right? So, for example, in the Euclidean case, of course, correlation 0 doesn't mean that they are independent already, right? So if you have one-dimensional data correlation, our measure is sort of an extension of the Euclidean correlation covariance measure, and of course, zero covariance, as we learn in statistics 1, doesn't mean anything about dependence or independence of the data. They can be highly correlated. They can be highly dependent, not correlated, but highly dependent in some way. So the covariance correlation measures are simplifications. So overall, a lot of the comments had been that basically important features are not reflected, which is true because the data are completely projected on sort of one-dimensional measures like inner products in the Hilbert space rather than the tensor product, right? So if we had some internal structural properties of our space, then we can take advantage of this and we should take advantage of it. We should also take advantage of the case where we have certain manifolds structure. In all of these cases, we can do much more than taking a simplified measure as we have done here. But there are problems with many of those proposals. First of all, the internal structure may not be known, or it's too complicated to evaluate. Typical example is manifold. You can, for example, think about covariances as random objects. They have, they usually, depending on the metric, have some manifold structure, but it can be extremely hard actually to decipher it. So a good approach in this case may be that you figure out what are the geodesics, what's the exponential and the log maps, and then operate locally on the tangent planes. But while this is standard in some metrics and very easy in the Frobenius case, it's very difficult in some of the more advanced metrics which have been recently proposed for covariances very specifically. There are just whole papers in mathematical journals which are investigating geodesics, log map and exponential map. If you can figure that out for some remote metric, you have already a paper in a mass journal. So the point is that some of those internal structures of those objects are very difficult to fathom and take a lot of work, while we have sort of an overall procedure that's a very simple extension from the Euclidean case, where we sort of go up in statistics with a covariance and correlation. And also the point about the robustness was an interesting one. We may be able to modify the procedure in this way to make it more robust potentially by, for example, trying to figure out if there are big distances that this may be outliers. So take some robust measures. That could be an interesting extension. So internal structure is ignored. We simplify the thing, we simplify everything big time. We get a Euclidean case as a special case, which I personally view as a plus in some applications. And we have interpretability, as the example shows. That may not be always true, but the examples we show, there is great interpretability of the Fréchet integrals and the Fréchet scores. The integrals work very well for mortality because it completely decomposes the variation which is actually in the sample. And the Fréchet scores worked well on the taxi data, where it shows, first of all, outlying occurrences, and secondly, gives you a separation of different days. So in some ways, the specific measures which can be derived can have great interpretability in data analysis. That's what we see. And it's clear that there is an arbitrariness in some way, because we can define, for example, the Fréchet scores in a different way. It doesn't have to be this way as we did. Namely, we use actually the eigenfunctions of the autocovariance operator to project the distances from the mean, which is a very coarse measure, on those longitudinally. So there was a comment about there is more structure, rotations and things like that are present. That's all true, but we sort of take the internal structure of the objects as a black box, so we don't know what they would be. So distance to the mean function you can have, but to think about rotations, which came up in one comment, is a difficult undertaking. So maybe future research can also look into some things which take sort of the some of the internal structure into account without going all the way to the manifold, even if it's present. So in some cases you can, but in other cases to go to the manifold is just extremely difficult. And so that's what I wanted to say, but you also have, I think.
So first I'd like to thank all the discussants for such nice thoughts.
Yeah,
so
I also like to join that.
So indeed, it's been very interesting to think about this project, because it's not very easy when you're not making any assumption about the structure of the space. But that's something we had in mind from the start, because so for example, like networks, they are manifolds. The graph Laplacians of networks are a submanifold in RD, but sometimes the manifold approaches also have problem because they depend on the local Euclidean approximation, which itself could be high dimensional. Like, suppose you have a 20-dimensional network and you want to work with the mean of the graph Laplacian, and if you're working with the Frobenius metric, then you have at least 190 unique entries, which gives rise, and if you have to test for means and also account for covariance in the tangent plane, then that is a very big dimensional covariance matrix, and estimation of that could be an issue in some applications. So our motivation to work only with the metric comes from the fact that we want to avoid any kind of structure associated with the space. So that means we make minimal assumptions, but then we do have to sacrifice something for that. So the sacrifice we make, as pointed out by the discussants, is that the covariance measure is collapsed because it loses a lot of information. But then again, there are some points, like For example, the principal components are now in the object space, and it may be interesting to study the change of variation in the objects in that space. Like usually for the kernel methods, or when we are not collapsing the covariance, we have the covariance itself is a big object, and we have scalar valued principal components. But here we are looking at how the networks vary. Suppose like if we have Fréchet integrals of networks, we would hope to identify through some suitable nice metric which points, which nodes in the network actually vary corresponding to which eigenfunction. So that, I think, is one of our points of interest as well in having scalar eigenfunction and an overall measure of variability. So I would like to say thanks, and I'm waiting to read all the discussions in more details and think about those in future.